Okay, review for our core competency final exam. As a reminder, this is the test that's put out by IEC National. So I don't actually get to create this test. All of our year ones across the nation are taking the same test. As a reminder, this is intended to be a 4-hour test, 80 questions long. It is going to cover anything from the beginning of the year until the end of the year. So anything is fair game, unlike our other midterms, our other finals where we only tested on that particular semester. This test is going to cover everything throughout the entire year. So with all that said, yeah, this is going to be a tough test, and it's intended to be that. And you can see in front of us here, we've got a pretty long list of potential topics. I went through the test. These are all the topics I thought were worth mentioning. Some we're going to spend a lot more time on than others. And at the same format as we did for the review for the midterm, I'm going to put up as many 15-minute videos as it takes. That way you guys can kind of watch them in small chunks. You don't have to sit down for some big long thing. You can watch them as you go. But yeah, here again, we'll dive right into this thing. We'll get done as many as we can in the first chunk here. I'm going to try to move at a pretty good pace. But the first one is circuit conditions, right? And this, essentially what are we talking about is, and maybe these pictures look familiar, but we have normal circuits, we have overloaded circuits, we have short circuits, we have ground faults, and we have open circuits. Those are the 5 main circuit conditions your text talks about, and these pictures come right out of the EWR textbook, I believe it is. But right off the bat, and I always find these pictures comical because they use the little smiley faces and frowny faces, but I feel like there's maybe a more mature way to do that. But anyway, still gets the point across. But your normal circuit, the moral of this one is your current is flowing in the normal path along your conductors, through your overcurrent protection, through your load here, which creates resistance. Normal circuit. We have no problem with that, right? But then we get into an overloaded circuit. An overloaded circuit means all the current still flowing in its intended path. Here we have 2 loads, but all the current is still flowing in its intended path. The only problem is we've overloaded our overcurrent protection device. In this case, these are rated 15 amps. We ended up with, they do the math here using Ohm's law, with almost 20 amps on this thing. So these fuses should trip, right? And the reason they give us our neutral face here is because, okay, the fuse is blue or the breakers trip, but otherwise everything's still safe. As long as those breakers or fuses do what they're intended to do, we're still safe. Whereas now we get down to a short circuit. This is essentially where a hot and a hot, another hot inadvertently come together, or a hot and a neutral inadvertently come together. So our current, our circuit, essentially takes a shortcut, right? In other words, the name short circuit, a shortcut for the current, where it kind of bypasses the load for some reason and goes straight from, in this case, it's an A phase and a B phase hot, but it could be a hot and a neutral, but it goes here and somehow around our load. So maybe somebody connected something they shouldn't have, or we inadvertently had a couple wires touched that shouldn't have. But that circuit sort of bypasses the load, takes a short circuit, or takes a shortcut, which is why it's called a short circuit, which means we have very little to no resistance that we would normally see if we went through the load. Now we have this really low resistance. Low resistance means a lot of current can flow. A lot of current flowing means, hopefully, it's more than enough to trip that breaker or fuse almost instantly. They calculate it to be 7,000 amps of current flowing because there's such small resistance. That's why we see that violent explosion and spark, because so much current flows in such a short time. But again, all that, those 7,000 amps should be going through the fuse of the breaker. That fuse or breaker should trip instantly. They give this one a nice little red sad face because we still get this violent explosion, right? Again, the breaker should trip and minimize the length of this dramatic situation, but it still occurs nonetheless. Then we get down here to a ground fault. Exactly the same thing, except in this case, instead of a hot to hot or hot to neutral, we're now basically doing a hot to ground. These are most common. Maybe somebody pinches a hot wire in between a metal cover when they're closing a box, or maybe a wire comes out of a wire nut and touches against a metal box. Most commonly, when you see a big, what most people would call a short circuit, it's actually a ground fault, right? And again, this kind of semantics here, that a short circuit is a ground fault. In the field, if I say, yeah, we had a short circuit, nobody's going to go, no, that was hot to ground. But if we're going to be technical about it, we should distinguish here, right? And then this one kind of drives me nuts, the last one, open circuit. So here we have everything's fine, looks just like the normal circuit, except somehow this becomes open. It becomes disconnected. If this were like a splice and somebody just opened it up, man, I'm not very happy about that. In fact, that's one of in my mind, the most dangerous situations here. Because if this is just open, it's not grounded or it's not touching another hot, it's not going to trip a thing. It's going to sit here like this until somebody or something touches it and completes that circuit or gives that a path to ground. Now, then again, maybe this is simply a switch that somebody turned off. That could be open as well. So it really depends on why we have that open circuit condition. But anyway, I wanted to refresh you guys on sort of the five main that the book talks about, the five main circuit conditions that we might encounter. So circuit conditions, keep those in mind. There's several questions around that information. Next up, we have our conductor identification. And what I mean by that is basically hot, neutral, ground. How do we talk about them? How do we describe them? And then color coding as well, you can see. So right off the bat, the official term is ungrounded conductor. When I talk about an ungrounded conductor, I'm talking about a hot is kind of the everyday name for that. We can color that thing any other color besides gray, green, or white. The reason for that, if you don't already know, is coming up here in just a second. Moving on to our grounded conductor, emphasis on the ED right here, grounded. The other common name for that is usually a neutral conductor. That can be colored white or gray, which is why our ungrounded cannot be colored white or gray. That's reserved for the neutral. And then following that same pattern, your grounding conductor, emphasis on the ING, is more commonly known as your ground. This is your ground in your circuit. When you pull a circuit, it's usually going to be that green conductor, or depending what type of cable, it could be a bare copper conductor, bare aluminum conductor as well. But there's your conductor identification, right? So moving down to derating. Now, here's one that I can tell you is all over this test. They are huge on derating conductors for whatever reason on this test. So this one is going to be all over the place. So right off the top, we need to know basically three tables. Your first is table 31016. Okay. That is the table that tells you what ampacity any wire is good for normally. Okay. On the left-hand side, we have our gauge. What size wire are we talking about here? Along the top, we kind of have two broad columns. The first is copper, which is these first three. The second then is going to be aluminum or copper clad, which is the second set of three. Then within the copper and aluminum sections, we have three more columns broken up. That is for 60 degrees, 75 degree, and 90 degrees Celsius conductors. That depends entirely on what type of insulation I use. Most commonly, we're going to use THHN insulation, let's say. I would find THHN in the 90 degree column right here. What that means is when I do my derating calculations, I'm going to say, what type of insulation do I have? I'm going to find it in whichever column. That's the column I'm going to use to start my derating calculation. I point that out because, and right at the beginning of the text, the beginning of this test, and I've said it before myself, if you're not told otherwise in this class, and we're just trying to say, what size wire do we need for this many amps? We're going to default to the 75 degree column. We're not going to do that when we're derating. That's going to be an exception to that rule. When we're derating, we're going to go as high as we possibly can. So if I have THHN and it's rated 90, I'm going to use 90. And we'll maybe see some reasons for that when we do some examples here in a moment. But anyway, 31016, that's going to tell you basically your ampacity to start with. What ampacity is any wire good to start before we do any derating? So then to answer the next couple questions, what other two tables do we need? We need to think about why would we derate? When I say derating, what am I even talking about? I guess we should say. And that is, again, any wire's good for this many amps to start with. But there may be certain conditions that say, hey, you know what? I'm not going to load it up to its full potential. It's only good for this many amps, which is going to be some less than what it started with. And there's two conditions when I would do that, or two that we study anyway. The first is if we have more than 3 current carrying conductors in a raceway. The second would be if we go in and if we install these in an area with a high ambient temperature. Both of those things, the common denominator for both those situations, more than 3 current carrying conductors, high ambient temperature, is the fact that it creates high temperature, right? Obviously, a high ambient temperature means our wires are going to be hotter. If I have a bunch of current carrying conductors in a pipe, they are also going to generate heat. Each current carrying conductor generates a little bit of heat. So jamming a bunch of them in together is going to generate even more heat, maybe a lot of heat. The common denominator is both things create heat or involve high heat areas. What happens to molecules when they heat up? Well, they expand. What is current flow? But it's basically electrons trading off from one molecule to the next. As those molecules get further apart, it's harder for those electrons to flow. That's another way to say it creates high resistance conditions, right? So heat creates higher resistance. So because of that, if a wire was normally good for 20 amps, we're going to have to derate it, and it's only good for something less than 20 amps, right? And here we have a little example that I threw out here. Let's say I have 4 number 12s, right? And let's forget about this math here. I'm kind of spoiling the ending a little bit. But let's say we have 4 number 12 conductors, and then we have 5 number 10 conductors. So we have 2 different size conductors we're dealing with. Then let's say we run them in an area that is 110 degrees Fahrenheit. What is our new derated ampacity for both conductors, for the number 12s and for the number 10s? So we're going to have to basically do 2 different calculations here. So the first question you got to ask yourself, and we're only talking about the current carrying conductors. The test is going to make that clear in the problem, but basically what that means is we don't count grounds. So I'm telling you now, we have 4 number 12 current carrying conductors. We have 5 number 10 current carrying conductors. That gives us a total of 4 plus 5, or a total of 9 current carrying conductors. So I have 9 current carrying conductors in this pipe, and they're in a 110 degree ambient temperature environment. So the first thing I got to do is check my table for more than 3 current carrying conductors. That happens to be 31015C1. If you guys find 31016, it's actually, I think, maybe 2 or 3 pages back from that in your code book. So just flip back a couple pages, you'll find 31015C1. That table tells us, depending on the number of conductors, I'm going to multiply it by this percentage. I just said I have 9 conductors, so the 7 to 9 conductor percentage is 70%. So I'm going to multiply my number 12, and I didn't tell you these are all going to be THHN copper, by the way. I'm going to multiply the ampacity of my number 12 by 70%. So what is my number 12 THHN copper good to start with? Here we have copper, here we have THHN. My number 12 is good for 30 amps to begin with, right? So this thing was good for 30 amps. I'm going to multiply it by, let's do this one. I'm going to multiply it by our 70% from our table here, which mathematically is 0.7, right? Come out with 21 amps, right? Now, to take that one step further, it's good for 21 amps. I'm in a high ambient temperature area of 110 degrees. So if I check my table over here, and we got to keep in mind, our ambient temperature is given to us in Fahrenheit. I'm going to use this column to find Fahrenheit. By the way, this is table 31015B1 at this point. I'm going to use this column to find Fahrenheit. If they've given me the ambient temperature in Celsius, I would use this side, but I'm using Fahrenheit here. So 110 degrees Fahrenheit is right here. It's an 0.87, an 87% multiplier. So I'm going to now multiply that 21 that I just got once again by 87%. So that number 12 is now only good for 18.27 amps, right? I'm going to do the same line of logic for my number 10. What is the number 10 good to start with? Up here we can see it's 40 amps. So we're going to take our 40 amps. We're going to multiply it by the same 80% that we did, the same 70% that we did up here. That's now only good for 28 amps. We're going to take that same 28 amps, we're going to multiply it by our 87%. From the temperature column, we get 24.36. So my number 10 is now only good for 24.36 amps. So that's kind of in a nutshell how we do our derating. Hopefully that all sounds familiar because, again, it is a review. But they hit that really hard on the test, so make sure you're pretty comfortable with doing that math.